In this video, we will discuss the net change theorem. This will be our first tool for applying calculus to the quote-unquote real world. First, let's look at a statement of the net change theorem from our OpenStax calculus textbook. You can read the statement on the screen or online. I will share insight into what this statement represents and how it can be interpreted. It says that the current value of a changing quantity is equal to the initial value of the quantity, plus the definite integral of the function giving the rate of change. In the theorem, big F of B represents the current value of the quantity we are interested in. Big F of A represents the initial amount of the quantity. And the definite integral of big F prime of x from A to B represents how much the quantity has changed over this interval. There is nothing special about the variable x here, and you will often see t as the variable, especially if the quantity is changing over time. To get started with physical examples, let's remember something we learned in Calculus 1. When we have a function that gives the position, aka displacement, of an object in terms of time, the derivative of that function will be the velocity of the object. We will use this fact to do this problem. Find the net displacement of a particle whose velocity function is given by v of t equals 5 times t minus 3 over the interval from 0 to 2. Since velocity is the derivative of displacement, we can use the net change theorem here. From the net change theorem, we see that the net change in position will be given by the definite integral from 0 to 2 of 5t minus 3 dt. First, we look at the integrand little f of t, which is equal to 5t minus 3. To evaluate this definite integral, we need to find an antiderivative for this function. We often call this antiderivative big F of t. In this instance, we look for an antiderivative of 5t, which is 5 times 1/2 t squared by the power rule for antiderivatives, and an antiderivative of 3, for which we can use 3t. So to find the net change in displacement over the interval from 0 to 2, we evaluate this antiderivative at the endpoints of the interval and subtract. This gives us big F of 2, which is 5/2 times 2 squared minus 3 times 2, minus the entire expression of 5/2 times 0 squared minus 3 times 0. When we simplify this expression completely, it is equal to 4. Now for an important part that often gets overlooked. What does that number 4 actually mean? Remember that we did this integral using the net change theorem to find the net change in position. So the position of the object changed by 4 meters from 0 seconds to 2 seconds. The object was 4 meters ahead of where it started. It's very important not only to be able to use the net change theorem to come up with an answer, but also to be able to explain what the final number means. Let's look at how we could have used computer tools to evaluate this definite integral. First, we will look at using Desmos. We first need to create a cell and define the function little f of t as 5t minus 3. Then if we create a new cell and type the letters int, Desmos will automatically create an integral symbol for us. We can put the numbers 0 and 2 in the upper and lower bounds and add little f of t and dt. As soon as we finish typing dt, we see the value of 4 pop up in the lower right-hand corner of the cell. We already knew that the answer was 4, but this confirms it. We can do something similar on wolframalpha.com. Here we can use the math input to select the integral symbol directly. However, when we select the equals sign to evaluate this expression, we get something weird. Wolfram Alpha is trying to interpret our integral as something about t3 speeds. This is where it's important to know that the variable of integration actually doesn't matter. So if the program we're using is having trouble with t, we can replace t with x in the integral and it represents the same thing.